Until now, we haven't considered a dielectric only filling part of the capacitor. We've been looking at parallel plate capacitors in situations where the space between the conductors is totally filled up by the dielectric. So what if we had a dielectric only filling up half of the capacitor like this? Or half of the capacitor like this? Does it matter how we fill up half? Does it actually make a difference? Or what if we were to fill up a capacitor like this, with materials of different dielectric constants? How do we deal with any of these scenarios? In this video, we're going to actually waive the mathematics and just present a sort of visual justification. Surely in a higher level physics class, you'll discuss the mathematics behind all this in the context of this thing called the electric displacement field, D. We're not going to concern ourselves with all that. Rather, we'll just present the consequences here and discuss how we use those consequences to approach solving intra-level problems. For all of these situations, we're going to make the simplifying approximation that the electric field is always perpendicular to the plates and only exists between the two plates. We've kind of been making that assumption throughout all of the videos here, but I just want to make sure we're on the same page. Suppose we had a dielectric filling up some space between the capacitors like this. We can turn a capacitor that looks like this into a configuration of capacitors in series, under one condition, however. If the original distance between the plates was d, and the distance that the dielectric took up was y, then our distances on these new capacitors in series look like this. The distance over here is of course y, and this distance over here is d minus y. We can't just use the original distance d because that distance has to get split up between our two series capacitors. However, keep in mind that the plate areas of each capacitor are the same, aren't they? The only geometric parameter that's changed for each is the distance between the plates. And this is our way of simplifying the original capacitor we had. We now just evaluate the capacitance of this new series configuration, one with a dielectric and one without, and we end up at our final answer. So you can now solve any partially filled capacitor problem that looks like this, but let's take it one step further. Now suppose we had a dielectric filling up the space between the capacitors like this. In this case, we can turn a capacitor that looks like this into a configuration of capacitors in parallel with one another. Under one condition, however, each of the new capacitor areas is smaller than the original area we started out with, because they have to add up to give you the total original area. So suppose the original area was L squared, just L times L for each side of a square plate. If the dielectric fills up a distance x, then the new area on one of the plates is L times x, while the new area on the other plate is L times L minus x. Notice that the distance d is still the same though, even after we split the capacitor. Now we have our new parallel capacitor configuration, and we know how to work with all of these components, so we can find the equivalent capacitance of this configuration, and that gives us a very good approximation for the capacitance of the original partially filled capacitor. Now we can solve any capacitor that looks like this, or any capacitor that looks like this. But let's crank it up a notch. Imagine we have a capacitor that looks like this. We now have multiple dielectrics at play, kappa 1, kappa 2, and kappa 3. So what do we do now? We apply the same simplification process we already know how to work with, but in an iterative or recursive way. That means we first have to apply our knowledge to create this parallel split here. Note that you have to take into account the change in area on each capacitor. After that, we apply our knowledge to create this split here. And we of course recognize that the original distance has changed for each of the new split capacitors here. And now we have something we can actually solve with the methods we've already learned. We just go about solving for this capacitor system the same way we would a normal configuration of series and parallel capacitors, and we end up with our final result.